But metals are very hard. It doesn't seem like this model will make a hard substance.
I'll take that one. You see, metallic bonds are very strong, but they're also flexible. This means they're malleable, which means that metals can be reshaped.
Well said, Mr. Bond. Shall we discuss the next type of bonding now?
Yes, I think we should.
I wasn't asking you! Mr. Bond?
Yes! Why don't we let the Chemeister explain this one?
Of course. Chemeister, will you explain covalent bonding?
We've talked about two metal atoms forming bonds. Now let's focus on two nonmetals. When most nonmetals bond to each other, they also share electrons. However, they don't share electrons as easily and freely as metals do. In general, most nonmetals only have the ability to share up to 8 electrons.
But what causes atoms to share the electrons in the first place?
Remember that the nucleus of every atom is positive, and that the electron clouds are negative. When positives and negatives get near each other, they attract. They get as close as they can, until the like charges of the two nuclei and the two electron clouds repel each other.
Okay, so the two atoms share the electrons equally?
No!
Dr. No, calm down. As it turns out, each element has a different power to attract electrons. This is called its electronegativity.
You can think of the bonding process as a tug of war. Very rarely do atoms pull with equal strength for the electrons. When they do, this is called a nonpolar covalent bond. Usually, atoms differ in electronegativity, and so one atom pulls more on the electrons than the other. This is called a polar covalent bond, since it creates two poles on the bond, a negative and a positive pole.
But wait, what happens when an atom wins the tug of war?
Then we get the third type of bond.
Right as always, Mr. Bond. The third type of bonding is between metals and non-metals, and it's called ionic bonding. In ionic bonds, one atom, usually the metal, loses its electron. When this happens, the atom becomes fully positive. The non-metal now has extra electrons, making it fully negative. You may recall that opposite charges attract, and that's exactly what happens here. The negative non-metal and the positive metal attract, becoming a very strong bond!
And here's something else to consider. Because these charges are so strong, they attract atoms from all around. When this process is completed, we get what is called a crystal lattice structure, a three-dimensional arrangement of charged atoms that form a very strong bond.
Excellent! We've discussed the three types of bonds and how they form. But there's one thing left to talk about. Intermolecular forces.
That sounds a lot complicated.
Well, it's not too bad. Just think of it as the bonding between molecules.
And a molecule is just a compound?
No! Although it's a common misconception, only covalent bonds form molecules. Metallic bonds and ionic bonds are made between large numbers of crystals.
So let's picture a typical covalent bond, a polar one. That means it has a negative end, and one end is positive. Now, if this molecule encounters another polar molecule, what do you think will happen? Well, opposites attract, so the negative end of one molecule will attract the positive end of the other.
Correct! And because two polar molecules are involved in this force, we call it a dipole-dipole attraction. In fact, this force is so strong, it's the reason water has such a high boiling point.
No! That's not all! When one of these atoms is hydrogen, and the other atom is very electronegative, this force is called a hydrogen bond. This is very strong example of a dipole attraction. And this is why water has such a high boiling point.
Technically correct, but this is still a dipole force.
The third type of attraction is called the London dispersion force. This occurs when two nonpolar molecules are next to each other. What happens is that for one instant, the electrons aren't shared equally, and one end of the molecule becomes negative for that instant. This causes a chain reaction where nearby molecules are caused to be slightly polar. This momentary existence of polarity results in a weak molecular attraction. Most gases, such as carbon dioxide, feel only this dispersion force.
But wait, couldn't a polar molecule also cause an instantaneous dipole?
You are correct, sir.
Who was that?
I don't know. But he should have mentioned that while polar bonds are also capable of feeling the London dispersion force, they don't really feel it because it's over so quickly. It makes it far weaker, and so we don't really consider it.
Well, folks, I think that's everything. You know the 3 types of bonds, you know how they form, and you know a little bit about intermolecular forces. How do you feel about your test now?
Positive!
Ready to do our dipole!
Electronegativity!
Combustion!
Ready to do our dipole!
You're so funny.
I wish he was my brother.